Welcome to lecture 2 for electric charges and fields. So we are beginning with two questions. First of all, let us solve the two questions that are based on the lecture 1. So we are dealing with the first problem. What is the force between two small charge spheres having charge of 2 into 10 to the power minus 7 coulomb and 3 into 10 to the power minus 7 coulomb placed 30 centimeter apart in air? So if we consider this kind of a problem, so this is the first problem which we are solving. So we are having something like this where the value of Q1 is equal to 2 into 10 to the power minus 7 coulomb and Q2 is equal to 3 into 10 to the power minus 7 coulomb, and the separation between them is 30 centimeter apart in air. So if we use Coulomb's law, so we can clearly write F equals K Q1 Q2 by R square, and over here I can write it as 9 into 10 to the power 9. Q1 Q2 can be written as 6 into 10 to the power minus 14 upon 30 centimeter can be written as 30 by 100 in meter square, and the value will be in Newton because we have written everything in SI unit. So we obtain a value equal to 6 into 10 to the power minus 3 Newton. And since the charges are of the same nature, the force will be repulsive in nature for both the charges. So the force will be repulsive for both the charges. Let us deal with the second question. So the second question is stating the electrostatic force on a small sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb in air is 0.2 Newton. The question is, what is the distance between the two spheres? What is the force on the second sphere due to the first? So if we begin solving this second problem, so we can solve it in this way. So we have a small charge which I am calling it as Q1, which is equal to 0.4 microcoulomb, that is 10 to the power minus 6 coulomb, and the another one is of minus 0.8 into 10 to the power minus 6 coulomb, and the force that is between them is equal to 0.2 Newton. The separation between them is not given. So if we approach using the Coulomb's law, that is F equals K Q1 Q2 by R square, so we can substitute the values, that is force is equal to 0.2 Newton, K is 9 into 10 to the power 9, Q1 Q2 can be written as 0.4 into 0.8 times of 10 to the power minus 12 upon R square. So from here we can calculate the separation between them, and the separation between them will be obtained as 0.12 meter. So the separation between them is 0.12 meter. The next one that is asked is, what is the force on the second sphere due to the first? Now as we have already learned that F21 vector is equal to minus F12 vector, so I can say that the force acting on both the spheres due to each other will be same. So the magnitude of force which the other sphere is experiencing is also equal to 0.2 Newton. The Coulomb's law is in accordance with Newton's third law of motion. So now we will be dealing with the next aspect on this lecture. So we will begin with writing Coulomb's law in vector form. So let us come to the Coulomb's law in vector form. So when we are dealing with Coulomb's law in vector form, so we will be dealing with it in this way. So we are considering a coordinate axis wherein we are considering that the position of the first charge is r1 vector, and over here a charge q1 is placed. The another charge is at a position vector r2 vector, where another charge q2 is placed. So I am drawing a dotted line joining them. So for the time being, I am considering this vector is in this direction. So the line joining them is from 2 to 1. So I am calling it as r21 vector, and we are considering that both the charges are positively charged. So if both the charges are positively charged, so from the vector law of triangle addition, I can say that if two vectors are in order, that is r2 vector plus r21 vector, then the resultant is the third side but in the opposite direction. So for this particular triangle, we will write it in this way, and from here I can calculate that r21 vector is equal to r1 vector minus r2 vector, and we are taking the magnitude of r21 vector as r1 vector minus r2 vector, and the line joining them as r21 cap, which is equal to r1 vector minus r2 vector divided by the magnitude, that is r1 vector minus r2 vector magnitude. So this is the value of r21 cap. So now if we will be considering the value of force that is acting between the two charges, so if we are calculating the force, so let us consider the force exerted by 2 on 1, which is in this direction. So we are calling it as F21 vector. So if I wish to write F21 vector in vector form, then we will be writing F21 vector as K Q1 Q2, that is product of the two charges, and the separation between them. So I am writing it as R square multiplied by R cap. That is the direction of R21 force or R21 vector. So if we express it out, so we can write it as K Q1 Q2, and R cap is in the direction of R21 vector. So we are writing it as R1 vector minus R2 vector divided by the magnitude of R1 minus R2 upon R1 minus R2 vector square. So from here we can write it as Q1 Q2 upon 4 pi epsilon naught R1 vector minus R2 vector by mod value of R1 vector minus R2 vector cube. So this is the expression of F21 in the vector form. If we wish to write F12, since the force is equal and opposite in nature, which we have already learnt in lecture 1, that F21 vector is equal to minus F12 vector. So we can directly write over here that F12 vector is going to look like Q1 Q2 upon 4 pi epsilon naught R2 vector minus R1 vector upon the mod value of R1 vector minus R2 vector cube. So this is going to be F21 and F12 in vector form. Let us move to the next aspect. So over here we are dealing with a small numerical where we will be establishing a comparison or a relation between the Coulomb's law and the Newton's universal law of gravitation. So if we look forward to understand this aspect, so as such We are not going to compare the two forces. We will just be looking at the similarity in the two equations. So if we look at the two equations, they look appear to very similar to each other. So considering this, I am writing over here the thing which we have previously learned, that is Newton's law of gravitation, and over here we will be having a look at Coulomb's law. So we are just looking at them in a comparison way as to how the two equations look similar. So the force between the two masses, that is m1 and m2, separated by a distance r, is given by F equals G m1 m2 by r square. And in case of Coulomb's constant or Coulomb's law, I'm extremely sorry, we take two charges q1 and q2 separated by a distance r, and we write the force or the magnitude of force between them as k q1 q2 by r square. Now over here, the if the comparison is done, we say that the force in case of the Newton's law of gravitation is always attractive in nature. The force exerted by 2 on 1 and the force exerted by 1 on 2 are still the same in this case also, that is F21 vector is equal to minus F12 vector. The force is the magnitude of both these forces is equal to G m1 m2 by r square. But the fact of the matter is this force is always attractive in nature. The two masses always attract each other, and the value of G is equal to 6.67 into 10 to the power minus 11, which is a very small constant in comparison to Coulomb constant. In case of the two charges, the force may be attractive or repulsive in nature. Force may be attractive or repulsive in nature, and the value of K is equal to 9 into 10 to the power 9, which we have already seen and used for quite some time, Coulomb to the power minus 2. So the value of electrostatic force constant, that is Coulomb constant, is much larger than the gravitational constant. And the large value of the electric force constant means that the interaction of even relatively small charges can produce significant force, which we have already seen. So this is the basic comparison between the two equations which we have. It must be kept in mind that the Newton's law of gravitation, that is the force is always attractive in nature, whereas in case of Coulomb's constant the force may be attractive, may be repulsive in nature. So let us solve a problem to understand it. We are asked to check the ratio ke square upon g MEMP is dimensionless. Look up at a physical constant and determine the value of this ratio. What does the ratio signify? So the parameter which is given to us is equal to ke square upon g MEMP. So this is the parameter that is given to us, where g is gravitational constant and k is Coulomb constant. So if we look at this from this point of view of dimensions or units, so the unit of the given ratio can be determined in this way, that the value of k is written in Newton meter square Coulomb to the power minus 2, and the two charges that is measured in Coulomb, so you write it as Coulomb square upon g, which is equal to Newton meter square kg to the power minus 2, and the two masses which is written in kg, that is kg square. So we see from here that the ratio which is given to us is dimensionless. So this parameter is dimensionless. So basically this ratio is of the electric force to the gravitational forces that is acting between the proton and an electron, which is separated by a certain distance. So what is being done over here is this, that maybe we can consider over here a proton having a plus E charge and an electron having a mass me and minus E charge separated by a distance small r. And if we apply the electrostatic force of attraction between them, then it is written as k q1 q2 by r square, and the gravitational force which is acting between the two masses is g me mp by r square. So if we look at the ratio of fe upon fg, so we can calculate it in this way, that is k e square upon g me mp. So since it is the ratio of the two forces, it is dimensionless. So if we calculate this value, that is the ratio of electrostatic force to the gravitational force, so we can calculate it as 9 into 10 to the power 9 into 1.6 into 10 to the power minus 19 whole square upon 6.67 into 10 to the power minus 11 into 9.1 into 10 to the power minus 31 kg, which is mass of electron, followed by 1.67 into 10 to the power minus 27 kg, which is the mass of a proton. So on solving this, we obtain a value which is roughly equal to 2.3 into 10 to the power 39. So with this, it is very much prominent that the value of electrostatic force is way larger in magnitude in comparison to the gravitational force of interaction between the two subatomic particles. Let us move to the next aspect. So in this we are going to discuss about the another concept which is regarded as superposition principle. So we are discussing about superposition principle. So now what does this imply? So if we say that there are a large number of charges that are placed together or close to each other, then the force on any one of the charge is given by the vector sum of all the individual forces exerted by each of the other charges. So for example, if I take a four particle system, so if I consider that there are four charges which is placed suppose on the vertices of a square, so we can consider them like this, and if suppose a force on one of them is arched, so if we are taking that the value of each charge is equal to plus q and the side of the square is equal to a, and let us suppose that we are calculating the magnitude of force on this charge. So the first force that we identify is equal to the force which is exerted by 1 on this charge, which I am calling it as 2. So force exerted by 1 on 2 is going to be kq square by a square. The another force which I identify on the 2 is due to 3, which is again equal to kq square by a square. And the third force which we are identifying is because of the fourth charge over here, which I am calling it as 4, and it is equal to kq square upon the separation between them is root 2a, so we are writing it as root 2a whole square. So these are the three forces which we have calculated for the the masses which is for the charges which is placed in the vicinity of this given charge. So according to the superposition principle, the net force acting on this particular charge is going to be the vector sum of all these forces, that is force exerted by 1 on 2 plus the vector sum of the force exerted by 3 on 2 and the force exerted by 4 on 2. So if we do the vector sum of all these forces, I can say that the force exerted by 1 on 2 and 2 on 3 are equal in magnitude, and hence the resultant of F12 and F32 will be in the direction of the diagonal line, and hence I can say that the net force is going to be root 2 times of kq square by a square plus kq square by 2a square, and it is in the direction of the diagonal, that is in this direction. So the direction of net force is in this sense. So the value of net force can be written as kq square by a square 2 root 2 plus 1 by 2 for a fourth charge placed on the vertices of a square. We are solving one more numerical over here. So let us deal with this numerical. Two identical small charged spheres, each having a mass m, hang in equilibrium as shown in the given figure. The length of the each string is L and the angle made by any string with the vertical is theta. We have to determine the magnitude of the charge on each sphere. So if I redraw this arrangement, so this arrangement is somewhat like this. So there is an insulated support and the two threads are involved which is supporting the masses having certain charge, that is charge q mass m. This one is also having charge q mass m, and the two strings are making an angle theta with the vertical. So if we consider this problem, the length of the string is given to us as L. So we can take the separation between the two charges as equal to 2L sine theta. So the separation between them is equal to 2L sine theta. So now if we start identifying the forces, so the first force that we identify, we can solve any one of the systems. So we are solving the left one. So it is going to be the force of electrostatic interaction between the two charges, and then there is a gravitational force, that is mg, or the weight acting in the downward direction, followed by the tensional force in the string, that is T. So if I draw its FBD, so we can draw it in this way, that this is equal to kq square by the separation between them squared, that is 4L square sine square theta. The weight mg is acting in the downward direction and the tensional force is going to be T. And if we take the angle theta, so we can take this angle as theta. So the component of tension can be broken as T cos theta, which is the vertical component, and T sin theta, which is the horizontal component. So we have these two components. So from here I can say that T cos theta is equal to mg, and we can calculate T, which is equal to mg upon cos theta. Now the next thing which I am writing over here is for equilibrium, the forces along y-axis must also balance. So this one is forces along x-axis, y-axis equating to 0. Now we are writing the next equation where we will be saying that forces along x-axis is also equating to 0. So we are writing kq square upon 4L square sine square theta is equal to t sine theta, and from here we obtain kq square upon 4l square sine square theta is equal to t can be written as mg upon cos theta into sine theta. So from here we need to calculate q. So we can put q over here, which is equal to, if we put k as 1 by 4 pi epsilon naught, we obtain q as 16 pi epsilon naught L square mg tan theta sine square theta's square root. So this is how the expression of charge is going to look like for this particular problem. Let us discuss another interesting concept now. So we are going to deal with the concept of electric field. So if we come to the definition of electric field, so we can say the electric field is the region where the influence of the charge or a charge system can be felt by any other external charge that is trying to come in contact with the given charge system. So it is regarded as the space around a charge in which its influence can be felt by any other charge particle. So if we try to understand it using the concept like this, that we can consider that there is a positive charge plus q, and we are taking a small test charge which is equal to small q, and let us say that the separation between them is equal to r. So if we calculate the value of force that is going to act between them, so I can say that the value of force that is going to act between them is going to be kqq by r square. Now to be very specific, we can say that the electric field vector at a point in the space is defined as the electric force acting on a positive test charge, that is small q, placed at that point divided by the test charge. So that is, from this definition I can frame that E vector is equal to limit q approaches 0 F upon q. So electric field due to the larger charge, that is plus q, can be calculated in this way, and hence we will end up writing that E equals kq by r square, and let us take a r cap in the direction of r vector, and we say that the value of electric field is directed away from the positive charge. So the direction of electric field vector will be same as that of the force vector. The magnitude of the test charge is kept small because otherwise it may disturb the original charge distribution, and then we will get electric field due to the disturbed configuration and not the original one. So this is the reason behind putting q approaches 0. I am repeating it one more time. The direction of E vector will be same as that of F vector. The magnitude of the test charge is kept small because otherwise it may disturb the original charge distribution, and then we will get electric field due to the disturbed configuration and not the original one. So hence we are saying that the charge is approaching 0. Now from here I can say that if a point charge is placed in an electric field, so we can say that it is going to experience a force which is given by F equal to q E vector. So if a point charge q is placed in front of a charge system which is producing an electric field E vector, then the force experienced by this small charge q is given by F equals q E vector.